I wanted to run through an example of using Kepler's third law of orbital motion to compute the length of the planet Neptune's year, namely how long it takes Neptune to go around the Sun. So here's the Sun, here's Earth, not to scale, and here's Neptune. And the distance between Sun and the Earth, we know, is 1 astronomical unit. The distance between the Sun and Neptune, you would have to look up. It turns out it's 30.1 times that, so 30.1 AU. Now we know from lecture, Kepler's third law says that p squared over a cubed is a constant for all planets in orbit around the Sun. It's the same constant for all of those planets, where p is the orbital period of the planet, namely the length of its year. A is the average distance between that planet and the Sun. So we ought to be able to use this to figure out what the length of Neptune's year is. Our first step will be to write Kepler's third law using the variables for Neptune. So we write that Pn squared over an cubed is constant, where the n subscript just refers to Neptune. And as I said before, that constant has to be the same for that ratio for Neptune as for the same ratio for the Earth. So we can also write that that constant equals Pe squared over Ae cubed. Well, the nice thing about this approach is that we know the values for Earth. We know the period of Earth around the Sun, and we know the average distance between the Earth and the Sun. So we can substitute in, for this ratio, 1 Earth year squared divided by 1 AU cubed, because 1 Earth year is the period of Earth around the Sun, 1 AU is the average distance between the Earth and the Sun. So that's nice. We've used Earth to pin down values that we know. Well, now we can just go through and solve for Pn, right? That's the period of Neptune, that's Neptune's year. So to do this, we'll multiply both sides of this equation by an cubed, effectively moving an cubed over to the right side of the equation. Now we'll plug in the value of an. We know that it's 30.1 AU. Now you have to cube the entire thing there, so this term here becomes this, and the nice thing is we can just enter that into a calculator, right? So you enter 30.1 cubed into your calculator, and it comes out 27,271. You also have to cube the unit, so it's now AU cubed. Well, the nice thing is we have AU cubed both in the numerator and in the denominator, so those are going to cancel. Namely, this term will cancel with that term, leaving us now Pn squared equals 27,271 times 1 Earth year squared. Now the answer is not 27,000 years. We've solved for Pn squared, but we want to solve for Pn, the orbital period. So to do that, we have to take the square root of both sides, of course with the understanding that this should be a positive number. Periods are always quoted as positive numbers. So now you enter the square root of 27,271 into your calculator, and that comes out to be, to 3 significant digits, 165. So our answer is 165 times 1 Earth year. That also had to go under the square root. 1 Earth year squared under a square root is just 1 Earth year. So that tells us that the answer is that the orbital period of Neptune is 165 Earth years. A few interesting things to note about this. One is that that's a really long time. 1 Neptune year is much longer than a human lifetime. So let's say that you move to Neptune, you want to celebrate your Neptunian birthday. Well, this is kind of depressing. You're not going to get a chance. You're not going to live to your first Neptunian birthday. I'm sorry. It's also the case that this number wouldn't have been very easy to come up with just in your head. People are sometimes inclined to think that things scale linearly, so if you're at 30.1 AU, maybe the orbital period of Neptune is 30.1 times that of Earth. But that's not true. What we had to do was we had to raise 30.1 to the third power and then take the square root. For most numbers, you can't easily do that in your head, so you really need to go through these steps and have a calculator handy to make sure that you get the right answer in the end.